Okay, now recording. All right, so we are here, right? Okay, I'm hoping to get up to 2.6 by tomorrow. Next week, 2.7 and 2.8 is all on derivatives. We'll be doing derivatives. Okay, and again, those of you who've had some background in calculus, you cannot use any of the shortcuts for derivatives. Okay, tomorrow's quiz is going to be on the epsilon delta kind of proofs from section 2.4. Okay, so just to let you know ahead of time. Okay, so I'll give you one of those proofs, show that the limit as x approaches a of f of x equals L, and use a definition using epsilon and delta. So you're given an epsilon, find a delta, and then go ahead and prove it just like we did in class, okay? So that's tomorrow's quiz. And it looks like our next test is the following Friday, the 26th. So now that you've already seen an exam, you know what all the exams are like. So chapter 2 material. So you know what that's about now. You turn all of this in. There's a 70% homework requirement. So if you don't turn in at least 70% of the homework, I don't grade your test. It'll count as a 0. Okay. And that's the way that will work. Okay, so that's where we're at. So I have a little bit of 2.5 left. I'll knock that off and then go on to 2.6 today and 2.6 tomorrow. And then we'll have our quiz tomorrow on the epsilon delta proofs from section 2.4. Okay. Quick word about the in-class yesterday. The question asks, where is the function discontinuous, not continuous? So you just needed to state the discontinuity points, which were -2, 0, and 3. Now, some of you put interval from negative infinity to -2 union, -2, 0, union 0, 3, union 3, infinity. That would be if it asks where the function is continuous, which is everywhere besides these points. Okay, so watch out how they word it. Okay, so you weren't supposed to, for this one, put negative infinity, -2, union, blah, 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 blah. Just -2, 0, and 3. That's all that was required for that in-class assignment. Okay. All right, getting back to and trying to knock off the rest of 2.5. Question 45. Okay, you were given a function f of x equals cx squared plus 2x. X is less than 2. And x cubed minus cx for x greater than or equal to 2. Okay. Now, they're trying to ask you for a c value, a value of c, where the function will be continuous everywhere. Okay, well, we already know the function is continuous everywhere except maybe at x equals 2. Regardless of the value of c, this is a polynomial, continuous everywhere. This is a polynomial, continuous everywhere. Okay? Since this is a piecewise defined function, the only way this can be continuous where there's not a jump, right? So you won't jump like this or like this. Okay? Then the only way that can happen is if these two match. Okay, so what do? I plug in 2 to both the top and the bottom and set equal. Okay, so if you see what, plug in x equals 2 for x. Okay, put a 2 right there, right there, right there, and right there. Okay, if the function is continuous at x equals 2, it's already continuous everywhere else. If it's going to be continuous at x equals 2, I have to get the same value here as here. Okay, so what you do is you plug in 2 and solve for c. So plug in x equals 2 to both the top and the bottom, set them equal, solve for c. So put a 2 right there, c times 2 squared plus 2 times 2, set it equal to 2 cubed minus c times 2. That's all. So just put a 2 everywhere you see x, like that. That's the top and that's the bottom. Now it's just some simple algebra. Okay, so that becomes 4c plus 4 equals 8 minus 2c. Add 2c over here, subtract 4. 6c is equal to 4. So c is 4/6 or 2/3. Okay, so that's all. Right, so one more time. For this, you want it to be continuous everywhere. So just plug in 2 for x and then solve for c. Put a 2 there, 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 there. Set the top equal to the bottom. Okay. Okay, then I was going to show you 49a. Let me show you the wording there. Which of the following functions has a removable discontinuity at A? If the discontinuity is removable, find a function g that agrees with f for all x not equal to A and is continuous at A. Okay, so what do they mean by that? Can you remove the discontinuity? Okay. Okay, so we talked before about a jump discontinuity. Here's an example of a jump discontinuity, right? There's no way this is going to be continuous no matter what I do. Okay, a removable discontinuity would be something that looks, let's say, like this. Okay, that's a removable discontinuity. Removable discontinuity, because you can just plug up the hole. Here, there's a jump. There's no way I can plug up the hole with just a single point. Okay, and remember, you're not allowed to draw a vertical line because then it's no longer a function. Okay, so this one at A equals 1, the function is not defined. Can we plug up the hole? And the answer in this case is yes. So a little bit of factoring on the top. X to the 4th minus 1 is x squared plus 1, x squared minus 1. Difference of squares. X squared minus 1 factors into x plus 1, x minus 1. And then we cancel these out. Okay, so we have x squared plus 1, x plus 1. Those are all ones there. Sorry, it didn't come out too good. Okay, again, very back on day number 1, quite often in algebra 1 we're sloppy, where we say this is equal to this. Not quite. They're the same everywhere except at A equals 1. You'd say, what's A? A is a particular value of x. You could just say x equals 1 also. Okay, so 1 is not allowed here, but 1 is allowed here. Okay, so how do I plug up the hole? Just plug in x equals 1. So we have a removable discontinuity at x equals 1. So they're asking us to redefine the function. Here it is. F of x is x squared plus 1, x plus 1. Okay, because whatever the graph of this looks like, it's exactly the same as this one, except there's a hole at x equals 1 here. Okay, so we have a removable discontinuity at x equals 1. Okay, so that's all. All right, then we're almost done except for the problems at the end, 53 to 56. And they deal with something called the intermediate value theorem, 53 to 56. And then I'm done, so let me show you that. Let's see. Check to chat quickly. Okay, I think we're good. All right, intermediate value theorem. So you can put this on your cheat sheet. It's on page 122. Intermediate value theorem. Okay, I might abbreviate with IVT. So if you see me write IVT, intermediate value theorem. Okay, suppose f is a continuous function on a closed interval from A to B. N is any number between f of A and f of B, where f of A is not equal to f of B. Then there exists a number C in the open interval from A to B such that f of C equals N. Okay, what does all that mean? Okay. Here is A comma f of A. Here is B comma f of B. And you have a continuous function. Okay, there's no jumps, no breaks. Okay, smooth all the way. Okay, so if you pick any number between this height and this height, somewhere it's going to touch the graph. That's the concept. Okay, like here's the picture. Okay, here's A comma f of A, B comma f of B. And you have a continuous function. No jumps, no gaps. So pick any number, they call it N. There's at least going to be one place which touches the graph. That's what they mean by there exists a number C. In this particular case, it looks like there's 2 possible, or maybe even 3 possible C's. C1, C2, C3 that touches the graph. Okay, but there has to be at least one. Okay, if I can use actual numbers, let's pretend this function value is 3. The height here is 3. This height is 10. Okay, then all the numbers between 3 and 10 are attained by the function. So if you pick 7 and 6.5 and pi, okay, and 9.3165214148828, okay, they're all going to be there. Okay, there's some number between A and B so that the function value is the funny number that I just said. Okay, it's called the intermediate value theorem. Okay, so you have a number here, they're not equal. Okay, pick any number between the two that is attained somewhere in the interval. Okay, in this particular case, they call it n. N has to touch 3 times here. In this picture, it looks like n touches just once, way over here. But you know, if it's smooth, right? If it's smooth going from, let's say I said 3 to 10, pick any number between 3 and 10, 6. Okay, somewhere, as long as there's no jumps, no gaps, okay, somewhere the function value is going to be 6. Same for 7, same for 8, and so on. Okay, now, more in particular to the problems that we have to do, suppose one of these is positive and one of these is negative. Okay, you can't see it here, but one's positive, one negative. That means if the function is continuous, somewhere the value has to be 0, right? Because 0 is between a negative and a positive quantity. Okay, that's the basic idea behind the homework problems, which I'll show you right now. So we only have 53 to 56. Use the intermediate value theorem to show that there was a root of the given equation in a specified interval. Okay, first thing I want to say is that you have to have 0 on the right hand side, like 53. And if it isn't 0, then you make it 0. Okay, and I'll be doing 54 and 56 for you because those are evens. Okay, it's actually not that hard. All you got to do is show that one endpoint's positive and the other is negative, and you have a continuous function. Therefore, somewhere there has to be a 0. Okay, so let me show you how to do that. 54, natural log of x is x minus square root of x between 2 and 3. So there's some number between 2 and 3 which makes this true. That's what they're saying. Okay, notice it doesn't tell us how to get it. We're not saying how to get this number, we're just saying it exists. So our first thing to do is throw everything on one side and make it equal to 0. So subtract that, add that. So ln x minus x plus square root of x equals 0. Okay, you have to have a 0 on one side. Okay. Again, if you're fuzzy about this, put this very example on your cheat sheet. That's fine. Okay, now I plug in 2 and I plug in 3. Okay, let's plug in 2. ln 2 minus 2 plus square root of 2. Punch in your calculator, it's about 0.107. Again, I won't take up class time to punch it in your calculator. You can punch it in a calculator as well as I can. Okay, f of 3, natural log of 3 minus 3 plus the square root of 3, which is about negative 0.169. There it is. That's what I want. One of them is positive. One of them is negative. Is this a continuous function? Yes, natural log is continuous, right? Polynomials are continuous. Square roots are continuous. The sum and difference of continuous functions is continuous. Okay, so therefore you have a continuous function. If you have a continuous function, okay, f of 2 is positive, f of 3 is negative, then that means somewhere in between there has to be a 0. Okay, so f is continuous. This says f of 2 is greater than 0. F of 3 is less than 0. So the language that they have is, so there is some number c in the open interval from 2 to 3 such that f of c is equal to 0 by the intermediate value theorem, IVT, intermediate value theorem. Okay, and here's a little mini picture of what's going on. So for this function, f of 2 was positive, right, 0.107. F of 3 was negative, negative 0.169. It's continuous. So how do I go from here to here in a continuous fashion? You can't jump and skip, okay? So in order for me to do that, you can delay it for quite a while, but sooner or later you have to cross the x-axis, right? Well, you might cross right away, but somewhere between 2 and 3, that's what they mean by the c. Okay? Somewhere between 2 and 3, f of c is equal to 0. Okay, essentially, if you say, I don't really know what you're talking about, all this stuff, to do these problems, all you got to do is show that one of them is positive and the other is negative, and then just write this language. Simplify it for you completely. Okay, just so one of them is positive, one of them is negative. Okay, and I'll do 56, and then that's it. That's the end of the section. Okay, show that sine x equals x squared minus x somewhere between 1 and 2. Okay, so there's a root, there's a solution somewhere. Notice it doesn't tell you how to get it. We're just saying that it exists. Okay, so throw everything on one side, subtract x squared, add x. So the function now looks like sine x minus x squared, that's a minus, plus x equals 0. That's my f of x. Okay, now the function is continuous. And let me raise it up again. 54. Okay, functions are continuous. Trig functions are continuous. Polynomials are continuous. The sum of continuous functions is continuous. Okay, plug in 1. I get sine of 1 minus 1 plus 1, which is sine of 1. Sine of 1 radian is positive. You can punch in your calculator if you want, but it's positive. Plug in 2. It's sine of 2 minus 2 squared plus 2. Sine of 2 minus 2. That's definitely less than 0. In fact, I don't even need a calculator for that. Okay, I already know that sine of anything is between -1 and 1, right? So if this is between -1 and 1, the biggest it can be is 1. But now if you subtract 2, it's definitely negative. Okay, so there it is. One side was positive, one side was negative. So just use this language. So there is a C in 1, 2. This is an interval, not a point. That's not a point in a graph. On the interval from 1 and 2, such that f of C is equal to 0. Okay, so that's how you do intermediate value theorem. Okay. Okay, do we ever have to put the exact values when figuring out the sides? In this case, you just need a decimal approximation. Okay, I mean, over here, if I look at it, I can't tell if it's positive or negative without punching in a calculator, right? Okay, and likewise for this. Well, this one you can survive without a calculator. I know that's negative, but yeah, just a calculator approximation is fine. Okay, what happens if there isn't a C? That's not going to happen for these problems. Okay, so for 53 through 56, there has to be such a C because one side is positive, one side is negative. That's what the intermediate value theorem states, that there has to be a C somewhere. Now, it doesn't tell us how to find it. Okay, we'll learn a technique for this a little bit later, section 4.8, I think it is. Okay, so, but for these, so you say, how do I don't know what you're talking about. How do I do the homework problems? Just show, we'll get everything on one side to be equal to 0. Okay, so I have no idea what you're talking about. Okay, get a function all on one side. Okay, so the only one that's set is 53. 54, 55, 56, throw everything on one side equal to 0. Plug in the left number, plug in the right number. Just show one is positive and one's negative. Okay, because if you show one is positive and one's negative, then by this intermediate value theorem, somewhere between them is a 0. So there has to be a so-called C, like over here somewhere. Okay. All right, so that's it for the intermediate value theorem. And I am now actually done with 2.5. So I'll get started with 2.6. Okay, so again, my goal is to finish 2.6 by tomorrow. Okay, 2.7 and 2.8 are all on derivatives. I'm going to go ahead and tell you ahead of time what formula or definition you want to use for the derivative. Okay, so make a note of this. In 2.8, page 152, definition of something called a derivative, box number 2 here. Okay, make a note of that. Now, frankly, if we were meeting on campus, I'd make you guys memorize it. Since we're not, maybe that's one nice result of the COVID situation we're in, that we're supposed to make it easier on our students. So, okay, you don't have to memorize it. So number 2, see that F apostrophe X? We actually say F prime, P-R-I-M-E. So we will say F prime of X. It's a definition of a derivative. Okay, so it's a limit as h approaches 0 of f of x plus h minus f of x all over h. We've actually done this expression already in our class. Okay, they were just setting you up from when we take your derivative. Okay, so what's derivative? I don't know what you mean. That's okay. I'll give you everything you need in time, but just telling you ahead of time. Here's the definition of the derivative that we'll be using. F prime of x stands for derivative. So that apostrophe f prime of x is a certain limit. Limit h approaches 0, f of x plus h minus f of x all over h. Now, when we calculate these, you're never going to be able to plug in directly. Can you see why? It says h approaches 0. Well, you can't plug in 0. So for all of these derivative ones, you have to do some derivative trick that we've seen before, right? Like rationalize the numerator or factor or something like that in order to get it to work. Okay. Now, if you look at the rest of 2.7 and 2.8, they give you lots of other definitions of derivatives. Okay, now, I'm not sure why Mr. Stewart gave you so many. You see 3 or 4 different ideas of derivative. They're all correct. But I figured out, why give you 2 or 3 or 4 different definitions of derivative? Just use one, the main one, and it's equivalent to all the others. Okay. So as you look at 2.7 and 2.8, you'll see other definitions of the derivative. Just use this one. Okay. All right, 2.6. Limits at infinity and horizontal asymptotes. Page 126. Limits at infinity and horizontal asymptotes. Okay, so let me show you the symbols that we have now. Page 127. Limit as x approaches infinity. Okay, you can also approach negative infinity. Limit as x approaches infinity of f of x is equal to L. So that means when x gets bigger and bigger and bigger and bigger, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, the function values does y approach any one number. Okay. So here's the picture right here. The limit as x approaches infinity of the function is 1. Okay. As x goes way out here, we get real close to the line y equals 1. In this case, it looks like the limit as x approaches negative infinity. Okay, negative 1,000,000, negative 1,000,000,000, we get real close to 1. I notice they give you a table. Okay, this happens to be an even function. Okay, so even functions have symmetry with respect to the y-axis. Okay, so the function was what? X squared minus 1 divided by x squared plus 1. And yeah, you can tell that if you plug in negative x, you get the same thing as if you plugged in x. That's why the table they got plus or minus. So this time you're not getting close to a number. Like when I say limit as x approaches 3, then you're going 2.9, 2.999, and 3.1, 3.01, 3.001. Okay. Now we're letting x get real big. So 1, 2, 3, 10, 50, 100, 1,000. Okay. So by the time you plug in 1,000, 0.999998. Okay, we're getting real close to 1. Okay. So we'll say that the limit is 1. Okay. And yes, you might be saying, oh man, do I have to make this table? No, there are much better ways than making the table. Okay. Neither you nor I feel like plugging in all these things, but you can see what happens in this case. Okay, so limit as x approaches infinity, you can also approach negative infinity. Page 128. Limit as x approaches negative infinity of f of x is equal to L. Okay, so look at the picture right here. Okay, so when x becomes very negative, right? Y approaches that red line L. Okay, so it goes out like so. And by the way, you can approach from above or below. Okay, so here it looks like you're getting a close, but it stays above. Here it looks like you're getting close, but it stays below. Okay, either way, we're going to say the limit as x approaches infinity or negative infinity equals the limit L. Okay, here's a graph. You actually may want to know this. You're going to see this quite a bit in this class and also Calc 2. Okay, the inverse tangent function. It's nice to know this function. Inverse tangent looks like this. It's bounded by pi over 2 and negative pi over 2. So if you look at equation 4 on page 128, okay, when x gets really big, we approach pi over 2. And when x goes to negative infinity, we approach negative pi over 2. Okay, so limit as x approaches negative infinity of inverse tangent of x is negative pi over 2. Limit as x approaches infinity of inverse tangent of x is positive pi over 2. So y equals negative pi over 2 and y equals pi over 2, it says just below that box, are horizontal asymptotes. Okay. So we're going to come up with horizontal asymptotes right now. So this is worth knowing. Okay. And again, if we were meeting face to face, I would actually make you memorize this, but there's a way to get around that since I'm letting you have a calculator. Okay. Just take inverse tangent of a huge number. Okay. And maybe I'll demonstrate that right now. See if I got my calculator here. Okay. So make sure that you're in radian mode. So let me check my mode. Okay. So yes, I am in radians. Okay. So if I do inverse tangent of a super big number, so I'll just put 1, 0, 0, 0, 0, 0, like that. Put 1 and then a whole bunch of zeros. 1.57. That's supposed to be pi over 2. Okay, let me actually type out pi over 2 now. Pi divided by 2. There it is. Every digit's the same. Okay, and then if you do inverse tangent of a negative big number, it should be negative pi over 2. So inverse tangent of negative 1, 0, 0, 0, 0, negative 1.57, blah, 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 blah. Okay. So in some sense, if you ever forget what the limit is, you're allowed to use a calculator and just plug it in. Okay. So when x gets super big, pi over 2, on this side, negative pi over 2. Okay. Okay. And one thing that you should know, okay, this is the basic idea that if you divide by a very big number, the number is very small, right? 1 over x to the r, where r is a rational number. Okay, so x squared, x cubed, doesn't matter. When x gets super big, the bottom gets super big, which means 1 divided by that, or any constant divided by that, approaches 0. Okay, and likewise, when I approach negative infinity, same thing. 1 over x to the r. Okay, 1 over x squared, 1 over x cubed, 1 over x fourth. If you plug in a super big negative, that's still going to approach 0. It doesn't even matter if the denominator goes to positive infinity or negative infinity. 1 over super big positive is almost 0. 1 over super big negative, like 1 over negative a billion, is a very, very, very tiny negative, but that's still roughly 0, right? Okay. Okay, so we're going to analyze some graphs. Okay, here's one thing, page 132. You should already be comfortable with this. The limit as x approaches negative infinity of e to the x equals 0. Okay, so you should know the exponential function looks like this. So when x approaches infinity, y approaches infinity. But when x approaches negative infinity, y approaches 0. And you got a little table here, right? So you look at the table, we get real close to 0. E to the negative 10 is puny, right? Okay, so what time is it? So 2.6, let's get started on some of this. So they're giving us all these graphs and we just need to analyze them. Okay, so let's see, we had to do 3 through 10. So I'll try to do the evens. Okay, number 4, unfortunately for 4, the questions are here, but the picture is here. So between moving back and forth and holding the book up, I won't be able to write. So sorry, so you just have to jot it down as I go along for these. Okay, so for the graph, got to put the book down. Got some kind of squiggle here, down like that, and like so. Okay. By the way, you might have heard about for an asymptote that you say the graph doesn't touch the asymptote. That's not necessarily true. Okay. So the graph approaches an asymptote, period. It might touch, it might not touch. So in other words, we're trying to say this counts as an asymptote. This also counts as an asymptote. An asymptote is a line that the graph approaches, period. Okay, somebody may have told you it's a line the graph approaches but doesn't touch. That's not true, although that's often true. Okay, it's often true, but not always true. Okay, so that counts as an asymptote. That counts as an asymptote. Okay, so let's see if we can get this. A, limit as x approaches infinity of the function. Okay, so when x gets super big, y approaches 2. So the answer to A is 2. Sorry, I won't be able to write it. But 4A is 2. B, limit as x approaches negative infinity. Okay, so I go way out to the left. Do the y values approach any number? Yes, looks like -1. So the answer to B is -1. C, limit as x approaches 0. And when it's written like that, let's see. Yeah, I don't see anything. So for C, is that 1 or 2-sided? Hint is to look at D and E. Right? D, there's a 2 with a minus. E, there's a 2 with a plus. C, there's no symbol. That means it's 2-sided. So you have to approach the same thing on both sides. Do we approach the same thing on both sides of 0? Yes, we do. On both the left and the right, it drops to negative infinity. So the answer to C is negative infinity. Okay, D, x approaches 2 from the left. E, x approaches 2 from the right. Okay, so 2, approach 2 from the left, approach 2 from the right. We approach 2 from the left, drop to negative infinity. Approach 2 from the right, positive infinity, right? Okay, so one more time, D is negative infinity, E is positive infinity. Okay, and then F, the equations of the asymptotes. So you have horizontal and vertical asymptotes. Okay, so horizontal asymptotes. So again, I'll be forced to just have you write it down. There's one here that would be y equals 2. So put down y equals 2 as a horizontal asymptote. I will abbreviate horizontal asymptote with HA, horizontal asymptote. There's another one here. So what is that? Y equals -1. Okay, so if you could write down, please, y equals -1 and y equals 2 are your HA's, horizontal asymptotes. And vertical asymptote, well, there's one here and one here. So VA, vertical asymptote, x equals 0 and x equals 2. X equals 0, x equals 2. Okay. Okay, 5 through 10, make up a graph that satisfies all the following conditions. Okay. So, oh yeah, let me go through this again in case some of you that don't plan on getting the book. Show you all the questions again. It's up to 10. More here. Raise it up. Up to 33-ish. Hopefully you can see that. And some more on this side. And yeah, I don't think we can do any of those. But 47 and 49, I think we had. And 51, 52. And we also had to do 61, 63, 65. Okay. Okay, number 6. Limit as x approaches 2 of f of x equals infinity. I'll just show you what I had. Okay, as x approaches 2, both sides, we go to infinity. X approaches -2 from the right, we go to infinity. X approaches -2 from the left, we go to negative infinity. Okay, so we approach -2 coming from the right, go to positive infinity. approach -2 from the left, we go to -infinity. That's what that said. The limit as x approaches -infinity of the function is 0. The limit as x approaches +infinity is 0, and f of 0 equals 0. Okay, so that means I put a dot at the origin. When x goes way out there and way out there, we approach y equals 0. So there's an example of the entire graph. Okay, and by the way, technically this can go down and then come back up. That's allowed, but this is the easiest, just to have it stay up here. Likewise, over here, it's allowed to come up and then go down. In fact, you can even come up and squiggle a while. Okay, but this is the easiest final graph. So here's the answer for number 6. Okay, and 8. Limit as x approaches infinity of f of x is 3. Okay, so when x gets real big, y approaches 3. So that's the example that I had right here, like so. Limit as x approaches limit as x approaches 2 from the left is infinity. Limit as x approaches 2 from the right is -infinity. So on this side, it says goes to -infinity. On this side, it says go to +infinity. And then it says f is an odd function. Okay, odd function. Okay, so far I have this. Odd function means symmetry with respect to the origin. Okay, so that means this thing is going to come down here. This thing reflects like so. So here's the answer to 8. Okay, looks like we won't have an in class today. I have too much material to come over. All right, and then 10. Limit as x approaches 3 of the function is -infinity. Limit as x approaches f of x, as x approaches infinity of f of x is 2. F of 0 is 0, and f is even. Okay, when we approach 3, the function approaches -infinity. Two-sided. Then it said when x approaches infinity, when x gets super big, the y values are close to 2. Okay, that's what it says right here. Right over here. F of 0 is 0. So I have this right now. And then it says the function's even. Even means symmetry with respect to the y-axis. So I just do the mirror image over here like so. Okay, so a quick review again. 6, 8, and 10. The odd ones, you should have the answers in the back of the book. Okay, now for some problems in finding the limits. Find the limit or state that it does not exist. Okay, so let me show you the technique for doing these problems. Limit as x approaches infinity of 3x minus 2 over 2x plus 1. Okay, if you plug in directly, this is a super big number. This is a super big number. Okay, so what's a super big number divided by a super big number? We don't know. Okay, the language we're going to use later is infinity over infinity. Okay, in other words, the top gets big, the bottom gets big. So how can you tell? So here's what you're going to do right now. Both of these are first degree, same degree. If they're the same degree, just divide top and bottom by x. Or if it were x squared, I would divide top and bottom by x squared. So Notice I raised up to 3x minus 2. I divided the top and bottom by x, like so. Okay. Then I do the division. So limit x opposed to infinity. Same game as before for limit. You have to keep writing limit, lim, x opposed to infinity, and so on. Okay. So what's 3x divided by x? 3 minus 2 over x divided by 2x over x is 2 plus 1 over x. And then here's the thing. When you see something like that or like that we talked about, right? When x gets super big, that approaches 0, that approaches 0. So when you see me write the arrow, I'll let you do likewise, but you don't have to. Okay, that's nothing, that's nothing. Plug in a billion. 2 divided by a billion is practically nothing. 1 divided by a billion is practically nothing. Okay, so it basically becomes limit as x opposed to infinity of 3 minus 0 over 2 plus 0, or 3 over 2. Okay, so the answer is 3/2. Notice again, in your final answer, you should not write limit anymore. Just write 3 over 2. Okay, now the problem's finished, but if you want to know, trade secret, I suppose, if these have the same degree, first degree, you pretty much just ignore these and just look at 3x divided by 2x, which is 3 over 2, right? The concept is when x gets super big, the -2 and the +1 drop into insignificance. Plug in a billion, 3 billion minus 2, it's basically 3 billion, right? 2 billion plus 1 is still 2 billion. Okay, if someone's a billionaire, they have $3 billion. They're probably not going to sweat, oh, I lost $2. They still have $3 billion. You have 2 billion and they get another $1. Okay, I'm glad, but I basically still have 2 billion. Right? So you just kind of cover this up and you say essentially it's 3 billion divided by 2 billion, which is 3 over 2. Okay. All right, 23, there's sort of a same thing going on, a certain trick to it. 23 looks like this. Okay, now, for super big X, we know the 2 is insignificant. You kind of feel like for super big X that 1 is insignificant also. So you have the square root of 4x to the 6, which is 2x cubed. In other words, it's almost like these are both x cubed, right? That's an x cubed, that's an x cubed. So how do we force that? So here's the trick this time. Okay, now remember over here, I divided top and bottom by x. Okay, we're sort of saying both of these are x cubed. This one has a square root though. So here's the trick. I divide top and bottom by x cubed, but in a funny format. Okay, do you agree that this is still x cubed? Right, the square root of x to the 6th underneath the radical. The square root of x to the 6th is x cubed. So this is a legitimate step. I did divide top and bottom by x cubed. The reason why you want to do that is now you can play the same game as over here and do the divisions. Okay, so limit is x opposed to infinity, 1 over x to the 6th plus 4, right? 4x to the 6th divided by x to the 6th is 4. Divided by 2 over x cubed minus 1. And there you have it. Now I have it the way that I want it. Okay, because now for super big X, plug in 1,000, a million, a billion, that's 0. That's 0. So don't have to write the limit anymore. Square root of 0 plus 4 over 0 minus 1. Square root of 4 is 2. So 2 divided by -1, which is 2. Okay. All right. Okay, so some of these are a little bit weird. 27, I wasn't going to do it, but I'll just give you a hint. Yeah, it should be a -2. Thank you. Should be a minus there. Did I put? I may have left off the negative. Thank you. It's -2. -27, I give you a hint, and then it sort of looks like the rest. (27) limit as x approaches infinity of radical 9x squared plus x minus 3x. My hint is to multiply top and bottom by the conjugate. Right? So the conjugate will be square root of 9x squared plus x plus 3x, top and bottom. Is that right? And you probably do the same kind of thing for something like 29. Okay, so 27 multiplied by the conjugate radical 9x squared plus x plus 3x. So let me just put that down as my hint. Multiply numerator and denominator by the conjugate. Okay, so if they're the same degree, just divide by that. So if they're both, x's, divide top and bottom by x. If they're kind of both x cubes, like this one, divide by x cubed. Now, what if they're different? Like this one. Okay, x to the 4th, x cubed. Okay, in this case, it actually doesn't matter. Okay, whether you divide by x to the 4th or x cubed. So let me divide top and bottom by x cubed and show you what happens. And then I'll be done with this since we're almost out of time. Okay, so divide the top and the bottom by x cubed. Like this. Okay, so what's x to the 4th divided by x cubed? X. Minus that divided by that is minus 3 over x. X over x cubed is 1 over x squared. Okay, on the bottom, x cubed over x cubed is 1. Minus that divided by that is minus 1 over x squared. That divided by that is 2 over x cubed. Okay, the main thing is that anything that has an x in the denominator, they're going to go to 0. Okay, so x becomes big, 1,000, 1,000,000, 1,000,000,000. That's nothing, that's nothing, that's nothing, that's nothing. You basically have x over 1. And what's x over 1? Just x. So what's the limit as x approaches infinity of x? Infinity. And again, that sort of hopefully gets your intuition. For super big x's, you forget about all these guys, right? These drop into insignificance. You have x to the 4th divided by x cubed, which is x. Okay, you're not supposed to do that. I mean, that's your intuition, but you're not supposed to do that as a proof. For the proof, you run through the stuff that I did over here. Okay. All right, so I see we're just about out of time. So we'll continue with this tomorrow. So tomorrow I'll do some more and be ready for a quiz on the epsilon delta stuff. Okay. All right, that'll do it for today, folks. So everybody have a good day and we'll see you next time. Okay, bye everyone.
Have a good one. Hey, can you put me in the attendance?